Welcome to the Sleepy Scholar. Settle in wherever you are. Loosen your shoulders, let the pillow take the full weight of your head, and let your breathing slow down to match the pace of my voice, which is going to stay soft and unhurried for as long as you need it to. There is nowhere to be tonight. Nothing to solve, nothing to finish, nothing to remember in the morning. If your eyes are still open, you can let them close now. Because everything I'm about to tell you is meant to be listened to with your eyes shut, drifting, the way you might listen to rain on a roof you don't have to fix. Tonight, we are going to travel a very long way, and we are going to do it very slowly. We are going to leave this room, and this house, and this quiet street. And we are going to go so far out into the dark that the numbers stop meaning anything ordinary at all. And I want to begin with a single point of light. Not a planet, not one of the familiar stars you might see through a window on a clear night. Just one star, alone, so far away that its light has been travelling toward us for almost the entire age of the universe. The astronomers gave it a soft old name. They called it Earendel. And Earendel is a single star whose light left it roughly 12.9 billion years ago. Let that number just sit there for a moment without trying to hold on to it. 12.9 billion years. The light that lets us see this one star set out on its journey when the universe was only about 900 million years old. A young thing, a newborn thing, only a few 100 million years past its very beginning. And that light has been falling through the black ever since, across a distance the mind cannot really picture, and only now, in our lifetime, has it arrived here to be caught. Here is the part I want you to hold gently as you drift. That star should be impossible to see. Truly impossible. There is no telescope ever built on Earth, and no telescope we have ever launched into space that is powerful enough to pick out one single star at that distance. A whole galaxy, made of 100 billion stars, is already a faint and difficult smudge at those distances. A single star, one lonely sun among all of them, is fainter than faint. It is beyond the reach of every instrument we own. And yet, we are looking right at it. We have its light. We know it is there. So how? How can we possibly be looking at something that every telescope we have should be blind to? The answer is the thing this whole quiet night is about. And the answer is that the universe, entirely by accident, built us a telescope of its own. A telescope far larger than anything human hands could ever assemble. Sitting between us and that ancient star is an enormous cluster of galaxies, a great crowd of galaxies bound together, and that cluster has a name too, WHL 013708. And that cluster of galaxies is bending and gathering the light of the star behind it, magnifying it, brightening it, focusing it toward us, until a thing that was invisible becomes visible. The cluster is acting as a lens light years across. And the long, thin, glowing streak of stretched light that the cluster smears the background into has its own gentle name as well. The astronomers call it the sunrise arc. And Earendel, that single impossible star, sits inside the sunrise arc, lifted into view by a magnification of not 10 times, not 100 times, but thousands of times. Without the cluster in the way, we would see nothing at all. With it, we see a sunrise from the dawn of everything. I want you to really rest in that idea, because we are going to spend the whole night unfolding it, slowly, one soft layer at a time. The idea is this. A cluster of galaxies can act as a lens, and not a small lens. A cluster is a lens that is quite literally light years wide, a natural magnifying glass so vast that no one had to build it, No one had to grind its surface or polish its curve. It simply is what it is, sitting out there in the dark. And it does something no human telescope can do. It takes the faintest, oldest, most distant things in creation, things hidden behind it, things we could never otherwise reach, and it swells them into view. We call these clusters natural telescopes. And that is not a poetic exaggeration, it is a working description of what astronomers actually do. They point our real telescopes not at the thing they want to see, but at a great cluster of galaxies, and they let the cluster do the heavy lifting. They use the cluster as the front lens. The cluster gathers the ancient light from whatever lies behind it and hands it to us, larger and brighter than it has any right to be. And the amount of magnification is genuinely staggering, so let me lay the numbers out softly, the way you might lay out smooth stones one at a time. A massive cluster of galaxies can magnify the things behind it by a factor of 10. That alone is remarkable, to make something 10 times brighter and larger for free. But it doesn't stop at 10. In the right places, along the right lines, the magnification climbs to 20 and to 50, and along a very special curve inside the cluster, a curve the astronomers call the critical curve, the magnification can leap to 100 times or even more. A 100-fold boost given freely by gravity along an invisible line drawn through a cloud of galaxies. There is no telescope humans have ever made, or could ever make, that would match a lens light years across. We simply cannot build something that large. But the universe already did. Now, I promised you we would go slowly. And I meant it. So let me pause here at the most natural question in the world. How? How on earth does a cluster of galaxies, a thing made of stars and gas and the great empty spaces between them, bend light at all? Light doesn't have weight the way a stone does. You can't push it around. So what exactly is happening out there in the dark to bring that ancient starlight curving toward us? To answer that, I have to tell you the most beautiful and I think the most restful idea in all of physics, and it comes from Einstein, from a theory he finished in 1915, a theory called general relativity. Now don't tense up at the name. There is nothing here you need to work at. I'm going to hand it to you in the softest possible form. We are all used to thinking of gravity as a pull. An apple falls because the earth pulls it down. The moon circles us because the earth pulls it close. That is how we are taught it, and it works well enough for apples and moons. But Einstein saw something deeper and stranger, and, once you feel it, far more peaceful. Einstein said that gravity is not really a pull at all. Gravity is a shape. Gravity is the shape of space itself. Here is the gentle picture. Imagine a large, soft bedsheet held out flat and level, the way you might smooth a sheet over a bed before sleep. Now imagine setting something heavy in the middle of it, a bowling ball resting in the center. The sheet sags, it dips down around the weight, curving into a bowl. The heavy thing has bent the surface around it. Now, if you were to roll a small marble across that sheet, the marble would not travel in a straight line. It would curve, following the dip, sliding along the slope the heavy ball had made. And you could say, if you liked, that the bowling ball pulled the marble. But that isn't what happened. The marble simply followed the curve of the sheet. It went straight as it could, across a surface that was no longer flat. That is Einstein's idea, and it is the whole secret of tonight. Mass, anything heavy, a star, a galaxy, a whole cluster of galaxies, bends the space around it, the way the bowling ball bends the sheet. And everything that moves through that space simply follows the new shape. Space is the sheet, mass is the weight, and the curving is what we feel as gravity. And here is where light comes in, and here is why the whole night hangs together. Light travels through space too. Light always takes the straightest path it can. But if space itself is curved, then the straightest possible path is also a curved one. The light isn't being pulled. The light isn't being grabbed or tugged or forced. The light is simply following the road it's given, and near a great mass, that road bends. Mass curves spacetime, and light follows the curve. It is not that gravity reaches out and yanks the light sideways. It is that the very road the light travels on has been reshaped, and the light, faithful as ever, follows the road. So let that be the image you carry into sleep. Light doesn't get pulled, light follows a road. And a heavy enough thing, a cluster of galaxies, can bend that road so much that the light of a hidden star comes curving all the way around to reach us. Now I want to slow down even further, because there is a detail here that I find genuinely lovely, and it is the detail that proves Einstein was right. It has to do with just how much the light bends, and with a quiet argument between two of the greatest minds who ever thought about gravity. You see, Isaac Newton, long before Einstein, had his own idea about gravity. Gravity as a pull, the older idea, the apple idea. And it turns out that even Newton's older picture, if you push it a certain way, predicts that starlight passing close to a heavy object should bend a little. So both men, in a sense, said light would bend near mass. But, and this is the exquisite part, they did not agree on how much. Einstein's theory, the curved space theory, predicts that light grazing past a heavy object bends by exactly twice as much as Newton's older picture predicts. Precisely double. A factor of 2. And that factor of 2 is not just a number, it is a fingerprint. It is the fingerprint of curved space. If light bent by the smaller amount, you might still believe gravity was only a pull. But if light bends by exactly twice that, if it bends by the doubled amount, then it is not being pulled at all. It is following curved space. The factor of 2 is the difference between a force reaching out to grab the light and the road itself being bent beneath it. So when astronomers went out to measure the bending, they weren't just checking whether light bends. They already suspected it did. What they were really measuring was whether it bent by Newton's amount or by Einstein's doubled amount. They were measuring which universe we live in. Let me give you the actual number, softly, because it is such a small and delicate thing to carry such a large truth. For light just grazing the very edge of our sun, skimming past the burning rim of it, Einstein's theory predicts a deflection of 1.75 arcseconds. And I know arcseconds mean nothing on their own, so here is the everyday picture. 1.75 arcseconds is about the width of a small coin, a coin you could hold between 2 fingers, seen from 2 miles away. Imagine standing at one end of a long stretch of countryside, 2 miles of open field, and someone at the far end holds up a coin, and you try to make out how wide it is. That impossibly tiny angle, that is how much the sun bends the starlight passing its edge. A whisper of a bend. A hair's breadth. And measuring that whisper is how we would find out whether Einstein or Newton had described the real world. So now imagine the difficulty. You want to measure how much the sun bends the light of stars passing close beside it. But the sun is blindingly, overwhelmingly bright. You cannot see faint stars right next to the sun drowns them completely, the way a lighthouse right in your eyes drowns out the candle beside it. On any ordinary day, the stars near the sun are simply invisible, washed away in the glare. So how could anyone ever measure the bending of a light you can't even see? There is only one way. You have to wait for the sky to go dark in the middle of the day. You have to wait for a total eclipse of the sun. You have to wait for the moon to slide perfectly in front of the sun and cover it completely, blotting out that terrible glare, so that for a few short minutes in the middle of the day the sky goes deep and dim, and the stars that sit close beside the hidden sun come quietly out. Only during those few minutes of a total eclipse can you photograph the stars right next to the sun and measure exactly where they appear to be. And that is precisely what happened on a day I want you to picture as clearly as a memory. The 29th of May, 1919. An astronomer named Arthur Eddington led expeditions to catch a total eclipse of the sun. The plan was patient and simple and enormously bold. During the eclipse, with the sun's glare blocked by the moon, they would photograph the stars that appeared close beside the darkened sun. Then, later, they would photograph those same stars again at night, months away, when the sun was nowhere near them and their light travelled to us in a straight, undisturbed line. And they would compare the two. If the stars near the sun appeared to have shifted ever so slightly from where they truly sat, if their light had been bent as it grazed past the sun, then the amount of that shift would tell the whole story. A small shift would mean Newton, a doubled shift would mean Einstein. And when Eddington measured the shift, when he compared the eclipse photographs to the night-time ones and saw how far the starlight had been nudged aside by the sun, the number matched Einstein. It matched the doubled bend. It matched curved space. The light near the sun had followed the bent road exactly as much as Einstein's theory said it must, and no more and no less. I want you to feel what happened next, because it is one of the few times in history when a piece of pure, difficult physics became something the whole world felt at once. The news went out, and it made Einstein world famous, overnight, not slowly, not among specialists, but overnight and everywhere. A man who had reimagined what space and time and gravity even are, whose theory had seemed to most people like beautiful, unreachable mathematics, was suddenly a household name across the entire planet. Because the sky itself had been questioned during a few dark minutes of an eclipse, and the sky had answered in his favour. The stars had moved exactly as he said they would, and the road light travels on was shown, for the first time, to be a bending thing. So rest here for a moment with me, at the very foundation, before we climb any higher. Everything we saw at the beginning of tonight, the impossible star Earendel, magnified thousands of times, the cluster acting as a lens light years across, the ancient light of the young universe swelled into view. All of it grows from this one gentle seed of an idea. Mass bends the road that light travels. A little mass bends it a little. The sun bends passing starlight by a coin's width seen from 2 miles off. But a great deal of mass, an unimaginable amount of mass, a whole cluster of galaxies gathered together, bends that road so profoundly, so deeply, that it can take the light of a single hidden star and curve it all the way round, focus it, gather it and hand it to us, magnified into something we can finally see. And I love that the same simple truth works at both ends of the scale. The sun bends starlight by a hair. A cluster of galaxies bends it into a great glowing arc. The physics is the very same, only the amount of mass has changed. It is like the difference between the small dimple your hand makes when you press it into a soft mattress and the deep, wide bowl that a person's whole body makes lying down. Same mattress, same yielding surface, Same simple sagging under weight, only the amount of weight is different. And the cluster is a very great weight indeed, pressed into the fabric of space, making a bowl so deep that light rolls down its sides and comes to us curved. Let me linger, because you're not going anywhere, and neither am I, on just how strange and wonderful it is that this works as a telescope at all. When you think of a magnifying glass, you think of a small disc of curved glass you hold in your hand, and you know that its curve is what does the work. The curve of the glass bends the light passing through it and gathers it, and that gathering is what makes small things look large. Now, a cluster of galaxies has no glass in it at all. There is no polished surface, no lens you could pick up. There is only mass, galaxies and gas, and something else we'll come to later in the night, and that mass bends the space around it into a curve. And the curved space does exactly what the curved glass does. It gathers the light, it focuses it, it magnifies. The lens is not made of glass, the lens is made of bent space, and that is why it can be light years across, because space is everywhere, and there is no factory large enough to grind a lens that size, but gravity makes one for free, wherever enough mass gathers. And so the whole practice of using these clusters as natural telescopes suddenly makes a beautiful kind of sense. If you want to see something so faint and so far away that your own telescope is helpless before it, you find a great cluster of galaxies sitting in front of it. And you let the cluster's bent space be the first giant lens, and your telescope becomes only the second small lens, catching what the cluster hands over. Astronomers pair their instruments with these cosmic lenses on purpose. They hunt the sky for massive clusters, they map exactly where the bending is strongest, and then they aim, and they wait, and they collect the ancient magnified light of things they could never otherwise touch. That is how we come to be looking at Earendel, a single star, 12.9 billion years of travelling light, a thing from when the universe was only about 900 million years old, a thing no built telescope can resolve. The cluster WHL 013708 sits in front of it, its bent space acting as an enormous lens, and it takes that one impossible star and lifts it into the sunrise arc, magnified by a factor of thousands, until the invisible becomes a point of light we can study and name. The star was always there, always shining, its light always crossing the dark toward us. But without the lens, that light would have arrived too faint to notice, a whisper lost in an ocean of black. The cluster gathered the whisper. The cluster made it loud enough to hear. I find something deeply calming in that, and I hope you do too, as you lie there, letting your thoughts go loose and slow. There are things in this universe so faint and so far that they seem lost to us forever, light too dim ever to reach us in any useful way. And yet the universe, without meaning to, without any plan, sets great lenses of bent space in front of them, and rescues that light, and delivers it. The oldest, dimmest, most distant glimmers of creation come to us not despite the great masses in the way, but because of them. The obstacle is the telescope. The thing standing between us and the ancient light is the very thing that lets us see it. Now, before we drift onward, I want to place one small stone of wonder in your palm, and then we'll carry it gently into the next stretch of the night. I told you that Einstein worked out all of this, that light bends, that space curves, that a great mass could act as a lens. He understood the mathematics of it more deeply than anyone alive. And you might imagine that a man who understood it so well would have been certain we'd one day see it, that he'd have looked up at the sky and said, of course, One day we'll photograph these rings and arcs. One day we'll use these lenses to see the dawn of the universe. But he didn't say that. Not at all. When Einstein finally sat down and worked out the precise geometry of a lens like this, the way a perfectly aligned mass would bend the light of something behind it into a ring, he wrote, in plain and almost sad words, that there was no hope of ever observing this phenomenon directly. No hope. He believed the alignment you'd need was simply too perfect ever to occur where we could catch it, and the light involved too faint ever to gather. He had found, in his own mathematics, one of the most powerful tools astronomy would ever possess, a way to see the faintest and oldest things in all creation, and he set it down, convinced it would never be anything more than a curiosity on paper. A beautiful idea, he thought, that the real sky would never show us. And here we are, looking at Earendel, a single star from the young universe, 12.9 billion years of light, held up before us by exactly the phenomenon, he said, we had no hope of ever seeing. The master was wrong about his own idea, not wrong about the physics. The physics was flawless. The light bends exactly as he said, by exactly the doubled amount, and Eddington proved it on that dark May morning in 1919. He was only wrong about us, wrong about what we would one day manage to catch. He thought the sky would keep this one hidden. The sky did not. So, keep that little stone with you as your breathing slows and the room grows soft and far away. The man who gave us the idea of the bending road, the curving space, the natural lens, that same man swore we would never see it work. And every clear night now, out beyond everything, great clusters of galaxies are bending the light of the hidden universe into rings and arcs, magnifying the faintest things that exist, and we are watching. We are watching the very thing he said there was no hope of watching. And in the parts of the night still to come, we'll see just how strange and generous that bending gets. How a single galaxy can appear in the same photograph more than once. How the light bends around things we cannot see at all. And how the same simple curve of space became not only our deepest telescope, but a clock for measuring the whole expanding universe. But all of that grows from the seed we've planted here. In the quiet, together, mass bends the road, light follows the curve, and the obstacle becomes the lens. Stay with me. There is so much more sky to drift through, and we have all the time in the world. Let me hold us here a little longer, though, in the warmth of what we've already gathered. Because there's no rush to move on and every reason to let it settle. Think again of that soft sheet and the weight resting in the middle of it and the gentle bowl it makes. Now scatter that picture across the whole of space. Everywhere there is mass, there is a dip. Around every star, a small dimple. Around every galaxy, a broad sag. And around a cluster of galaxies, hundreds of galaxies, thousands of galaxies, drawn together into one great crowd, there is a vast and deep depression in the fabric of everything, a valley in the shape of space itself, wide enough that light passing anywhere near it rolls down the slopes and is turned. That is the natural telescope, not a machine, a valley in space. A place where the road bends because something heavy is resting on it. And the light that comes to us through such a valley has travelled a curved path to reach us, which means the picture it paints is a strange and stretched and doubled thing, unlike any photograph you've ever seen taken here on Earth. The hidden galaxies behind the cluster don't appear as neat little ovals. They appear smeared, drawn out into long, thin arcs, curved around the heart of the cluster like brushstrokes bent by an invisible hand. The The sunrise arc, where Earendel lives, is exactly such a brushstroke, a background galaxy, pulled and stretched by the bending of space into a long luminous curve, and within that curve, magnified beyond all reason, one single ancient star made visible. When you look at the images these clusters give us, you are not looking at the sky the way it truly is arranged. You are looking at the sky as the bent road delivers it, stretched, curved, magnified, sometimes repeated. It is the true light of real and distant things, but folded through a lens light years across, and it carries the signature of that folding in every arc. And I want you to sit with the sheer scale of the gift, because it is easy to say magnified 100 times and let the words slide past. 100-fold magnification along that critical curve inside the cluster means 100 times more of the ancient light gathered and delivered to us than would otherwise arrive. It means seeing 100 times deeper into the faint. It means the difference between a thing being forever lost in the dark and a thing being bright enough to study, to measure, to name. And it costs us nothing. We did not build it. We did not power it. It has been sitting out there for billions of years, quietly gathering the light of the young universe, waiting for anyone to come along and look through it. And when at last we did, when we finally aimed our own small instruments through these enormous valleys of bent space, we found the dawn of creation waiting on the other side, magnified and ready. There is a tenderness in that which I never quite get over, and I hope, as you drift here in the dark, it reaches you too. The universe made us telescopes we could never build. Out of nothing but weight and the yielding of space, and it aimed them, entirely by accident, at its own most ancient light. And a man once said there was no hope of ever seeing through them. And now we see. So breathe slowly, and let the number 12.9 billion drift by without weight, and let the little star called Earendel hang there in your mind, held up by a lens light years wide. Shining from the young morning of the universe, we have followed the road all the way from a coin seen 2 miles off, past the darkened sun of a 1919 eclipse, out to the deep valleys of bent space where whole clusters gather the oldest light there is. And we are only just beginning. Rest here. The road bends on, and we will follow it, slowly, together, into everything that comes next. That man, incidentally, was Albert Einstein. And the story of how he came to write down the very geometry we have been describing, and then immediately declared it pointless, is one of the quieter, stranger chapters in the whole history of science. It is worth sitting with, because it tells you something not just about the phenomenon, but about how even the sharpest mind alive can look at a correct answer and fail to see what it will become. The year was 1936. Einstein was 57, already legendary, living in Princeton after fleeing Europe, and he received a visit from a man named Rudi Mandl. Mandl was not a physicist in any professional sense. He was an amateur, an enthusiast, the kind of person who reads deeply into a subject out of pure, stubborn love for it, and then has the audacity to walk up to the foremost scientist of his age and say, essentially, "Have you considered this?" Mandl had been puzzling over whether light from a distant star, bending around a nearer star, might be focused the way a lens focuses light, and whether this might produce a visible ring. He pressed Einstein on the question. He pressed him, by some accounts, quite persistently. Einstein, who was by then thoroughly occupied with other problems, apparently worked through the mathematics to satisfy Mandl and put the matter to rest. He found that yes, If a background star, a foreground star, and the observer were aligned with perfect precision along a single straight line, the light of the background star would bend around all sides of the foreground star equally, and the result would be a ring. A thin, luminous ring hanging in the sky around the lensing star, the background light spread into a halo. He worked it out. The geometry was clean. And then he wrote it up, briefly, reluctantly, and published it in the journal Science in 1936. The paper was short, almost dismissive. In it, Einstein thanked Mandel for the idea, explained the geometry, derived the angular size of the ring, and then wrote, plainly and with what seems to have been genuine feeling, of course, there is no hope of observing this phenomenon directly. Read that again. The man who predicted the effect, whose name is now permanently attached to the ring, believed, at the moment of publication, that no one would ever see one. He thought the alignment required was too precise to occur in nature with any useful frequency. He thought the background stars would be too faint once their light was spread into a ring. He thought the ring itself would be too small, too dim, too improbable. He published it as an interesting geometric exercise and expected it to stay that way. There is something quietly humbling in that. Not a failure of intellect, Einstein's calculation was exactly right. The geometry he derived in that short, reluctant 1936 paper is the same geometry astronomers use today. The humility is in the vision. He could see the form of the thing perfectly and still fail to see what it would do, where it would appear, how extravagantly common it would turn out to be once you looked in the right direction with the right eyes. The thing he dismissed as a curiosity is now one of the most productive tools in modern astronomy. It is on the first image released by the most powerful space telescope humans have ever built. Before we leave Einstein's paper, one more thread. It was not quite the first time anyone had noted this ring effect in writing. A physicist named Orest Coulson had observed the same geometric possibility back in 1924, 12 years before Einstein's paper, and had sketched the idea of a double image or ring that might appear when two stars aligned. Coulson's note was brief and largely ignored at the time. The effect is sometimes credited to him in older literature, the Coulson ring, though the name Einstein ring is the one that stuck, partly because Einstein's 1936 paper worked out the geometry more fully, and partly, one suspects, because Einstein was Einstein. These priority questions in science are often like that. The credit drifts toward the name already in the room. But what Coulson in 1924 and Einstein in 1936 were both thinking about was stars. Individual stars bending the light of other individual stars. Single points lensing single points. Small, precise, requiring an alignment so exact that finding it in nature seemed more like a dream than a program. Which is why neither of them predicted what was about to happen to the idea, what one man, working around the same time, was already arguing with characteristic ferocity would be the real and useful application of the effect. That man was Fritz Zwicky. And if Einstein was the reluctant mathematician of lensing, Zwicky was its prophet. Zwicky was Swiss-American, a physicist at Caltech, and he had a reputation for being difficult, combative, sometimes brilliant in ways that took his field decades to catch up with, and frequently right about things he had absolutely no business being right about yet. He was the kind of scientist who seemed to reason ahead of the available data, and then spend the rest of his career watching the data slowly confirm what he had already said. He had a particular relationship with invisible mass. In 1933, 3 years before Einstein's reluctant ring paper, Zwicky had been studying the Coma Cluster, a great congregation of galaxies far out in the universe, and had noticed something that should have kept everyone up at night. The galaxies in the Coma Cluster were moving too fast, dramatically too fast. If you added up all the mass you could see, all the stars, all the glowing gas, everything that emitted light, the gravity it generated was nowhere near enough to hold those galaxies together at the speeds they were moving. The cluster should have been flying apart. It wasn't. Zwicky concluded that there must be far more mass than anyone could see, mass that did not shine. He called it dunkel materie, dark matter. He published this in 1933, and for the most part the physics community glanced at it and moved on. The idea was too strange, the evidence too indirect, the whole notion too uncomfortable. Invisible mass? What would that even be? Zwicky went on being right about it anyway. Then, in 1937, a year after Einstein's ring paper, Zwicky did something that in retrospect deserves far more attention than it usually gets. He read what Einstein had published, set aside the single star framing, and immediately grasped what Einstein had missed. Einstein was thinking small. Zwicky thought large. He published a short paper in Physical Review arguing that the real lenses would not be individual stars. They would be galaxies. Whole galaxies containing hundreds of billions of stars each, stacked into clusters containing hundreds of galaxies. Masses so stupendous that their lensing effect would not be a delicate ring around a single faint point, but a gross, visible distortion of the sky visible across enormous distances. Zwicky's 1937 paper made 3 predictions. First, galaxies used as lenses would let us see objects far fainter and more distant than we could otherwise observe. They would act, in his words, as natural telescopes. Second, by measuring the geometry of the lensing, we could directly weigh the lensing galaxy, dark matter included, without having to make assumptions about what it was made of. Third, lensing would provide an independent test of general relativity on scales much larger than Eddington's solar eclipse. He was right about all 3, every single one, and he said so in 1937, 42 years before anyone confirmed the first real gravitational lens, and 85 years before JWST would take the image that most vividly proved it all. The field largely ignored him. Again, there is a melancholy rhythm to Zwicky's career that I find myself thinking about in these quiet hours. He saw the dark matter in 1933. He foresaw the lensing telescope in 1937. He was prescient about neutron stars, about supernovae as cosmological tools, about a dozen things that came true long after he had stopped being in the room to receive the credit. He was also, by most accounts, genuinely difficult to be around, which did not help his ideas travel. Science is a human enterprise, and human enterprises carry all the frictions that entails. But the ideas themselves were real, and they waited, patient as everything in the universe is patient, for the instruments and the attention to catch up. Meanwhile, the question of what actually makes a full Einstein ring, as opposed to a partial arc or 2 separate images, or nothing visible at all, is worth sitting with gently here. Because the geometry is clean and lovely once you have it. Imagine a background galaxy, very far away. Between you and it sits a massive foreground galaxy, much closer. Now imagine drawing a perfectly straight line from you through the center of the foreground galaxy and out to the background galaxy behind it. If those 3 things, you, the foreground galaxy, and the background galaxy, sit exactly along that line, then the light from the background galaxy bends equally in all directions around the foreground mass, and what you see is a complete ring, a thin, unbroken circle of light centered on the foreground galaxy. The entire background source spreads symmetrically around the lens. That is the Einstein ring. In practice, the alignment is almost never perfect. In practice, you are rarely sitting at the precise point where the line runs straight through. So what you get instead is a partial arc. The background galaxy's light bends more on the side where it passes closest to the foreground mass, and that side brightens and stretches into a long curving smear. The other side may produce a fainter, smaller arc, or just a faint second image. The further off-axis you are, the less perfect the alignment, the shorter and less symmetric the arc. A very slightly off-axis alignment gives you two separate images of the source, one on each side of the lens. A moderate alignment gives you partial arcs, and only the rarest, most precise alignments give you the full, unbroken ring. The size of whatever ring or arc you see, specifically the angular radius of an Einstein ring, has a name, the Einstein radius. It is not arbitrary. The Einstein radius depends directly on the mass of the lens and the distances involved, and the relationship is precise. The Einstein radius scales with the square root of the lens's mass. A heavier lens produces a wider ring, which means that if you can measure the ring, if you can see it clearly enough to mark its angular size in the sky, you can work backwards and calculate how much mass is doing the bending. Not just the mass you can see, the total mass. Stars, gas, dust, and all the dark matter that Einstein himself never quite grasped would be the dominant player. The ring tells you the whole ledger, not just the glowing entries. There is one more elegant test worth knowing, because it is part of how astronomers confirm they are looking at a real lens rather than something else. Gravitational lensing is achromatic. That word means it works the same way for every color of light, every wavelength of the electromagnetic spectrum, from radio waves to X-rays and everything between. Gravity doesn't have a favorite wavelength. It bends blue light and red light and infrared and radio by exactly the same amount. So a genuinely lensed arc or ring will look identical no matter what kind of light you observe it in. The smear will fall in the same place on a radio telescope image and on an optical image and on an infrared image. That cross-wavelength consistency is the fingerprint. Other things can produce elongated blobs in the sky, coincidental alignments of unrelated galaxies, tidal tails from collisions, shreds of gaseous material, but very few of them look identical across the full spectrum the way a lensed image does. The achromaticity is the tell. It is the thing that lets you rule out the mimics. And so by the late 1970s, astronomers had the theory. They had Einstein's geometry, correct and precise since 1936. They had Zwicky's vision of galaxies as lenses, ignored since 1937. They had the alignment conditions, the Einstein radius, the achromatic signature. They had all the conceptual scaffolding in place. What they did not yet have was one single confirmed example. That changed in 1979. The year is worth marking, because it was not a glamorous discovery of the kind that fills press releases with exclamation points. It was, in a certain sense, an accidental one. A recognition that something already in the data was something nobody had thought to look for. 3 astronomers, Dennis Walsh, Robert Carswell, and Ray Wayman, were studying what appeared to be 2 quasars sitting very close together in the sky. Quasars are extraordinarily luminous objects, the brilliant cores of distant galaxies, powered by supermassive black holes devouring enormous quantities of material and blazing with the energy of trillions of suns. This pair, catalogued as CUSO ERO 957 plus 561, lay in the direction of the constellation Ursa Major. Two bright points, close together, more or less the same brightness, more or less the same colour. Walsh, Carswell, and Wayman took spectra of both. A spectrum is a kind of fingerprint. It spreads the light out by wavelength and shows you the chemical and physical signature of the source, the specific dark absorption lines and bright emission lines that identify what a thing is made of and how fast it is moving away from you. If two quasars are genuinely two different quasars, their spectra will differ. They will have different fingerprints, different distances, different compositions, different redshifts. These two had identical spectra. Not similar. Identical, same redshift, same absorption lines, same emission lines, same everything. And between them, in the direction that the lensing geometry demanded, sat a foreground galaxy. What they were looking at was not two quasars. It was one quasar, its light split into two images by the gravity of an intervening galaxy, each image taking a slightly different curved path around the lens to reach the telescope. The twin quasar. The first confirmed gravitational lens, almost 42 years after Zwicky's prophecy and 43 after Einstein's reluctant paper. And so the era began, not with a ring, not yet, but with two bright points that turned out to be one, two reflections of the same distant fire caught by the same gravity on the way to the same eye. It seems right, somehow, that the first confirmation was quiet like that, not a dramatic arc blazing in a telescope image, but a double fingerprint on a strip of spectral data. The recognition of a sameness where a difference should have been. 6 years later came the Einstein cross. The year was 1985, and the object was a quasar called Q237 plus 0305, also known as Hucra's lens, because the foreground galaxy was in a catalogue compiled by the astronomer John Hucra. What made this one startling, what gave it the name it carries, is that the light of the background quasar split not into two images, but into four. 4 points of light arranged in a neat cross pattern, symmetric around the core of the foreground galaxy sitting at the centre. One source, 4 paths, 4 images. The Einstein cross is one of those objects that, once you understand what you are looking at, feels almost theatrical in its precision, as if the universe had decided to demonstrate the geometry as clearly as possible, not for its own purposes, but for ours. Why 4 and not some other number? The geometry of lensing is a rich subject, but the short answer is that the number of images depends on the shape of the lens and the exact position of the source behind it. A point source behind a perfectly circular, perfectly smooth lens produces a ring when aligned perfectly, and 2 images when not. But real lenses, real galaxies, are not perfectly circular or smooth. They have clumping, asymmetry, mass distributed in complicated ways. Those irregularities allow for more exotic configurations. A source sitting in just the right place behind an asymmetric lens can have its light split into 4 separate paths, arriving at 4 separate points on the sky. And there is a beautiful theoretical result hiding in the mathematics here, the odd number theorem, which states that a smooth, transparent lens always produces an odd number of images in total. 5, not 4. But the fifth image, the one that would sit right at the center, right behind the brightest, densest part of the lensing galaxy, is almost always squashed so faint and so small by the lens's core that it vanishes entirely beneath the glare. We see four because the fifth is swallowed, a ghost image behind a ghost mass. Meanwhile, a different kind of discovery was happening in galaxy clusters. Remember that Zwicky's real insight was not about individual galaxy lenses, but about clusters, whole congregations of hundreds of galaxies, their combined mass so enormous that their lensing effect would be visible on scales no single galaxy could manage. By the mid-1980s, astronomers with good enough telescope time were beginning to look at clusters carefully. And what they found there was different from anything the quasar work had produced. They found arcs, not points, not crosses. Great curving smears of blue-white light stretching across the images of clusters, shapes that didn't fit any galaxy morphology anyone recognized. The first giant arcs appeared in images of two clusters, Hubble 370, and a cluster called CL 224402. The discoveries came in 1986 and 1987 from work by Roger Linz and Vahe Petrosian, and independently by a French team including Geneviève Sucal. These were not tidy cross patterns or discrete double images. They were long, luminous stripes, curved as if drawn around the cluster's mass, spanning what seemed like extraordinary distances in the sky. There was initial confusion about what they were. No one had seen anything like them before. Were they tidal features, streamers of gas pulled out from colliding galaxies? Were they some exotic new type of object inside the cluster? Were they artifacts of the imaging process? The question took time to settle. For Hubble 370, the answer came from spectra. The arc in Hubble 370 is a magnificent thing, long and blue and curling across the image of the cluster like a pale crescent, so visually striking that it earned a name, the Dragon. Astronomers took spectra of the Dragon in 1988, and the spectrum showed that the light of the Dragon was coming from far behind the cluster, from a galaxy at a completely different distance, a completely different redshift. The Dragon was not part of Hubble 370. It was a galaxy behind Hubble 370, magnified and stretched by the cluster's gravity into a luminous curving smear that happened to look, in the cluster image, like a great blue arc. A background galaxy, dressed up in the cluster's light, bent into the shape of a dragon by 1 billion years of invisible gravity. That was 1988. And 1988 was also when the first truly complete Einstein ring was confirmed. The ring was a radio source, not visible light this time, but radio waves, the long, languid wavelengths of the electromagnetic spectrum that carry their own kind of information about distant objects. The ring was catalogued as MG1131 plus 0456, and it was detected by a team including Jacqueline Hewitt using the Very Large Array Radio Telescope in New Mexico. A ring. A complete, closed ring of radio emission surrounding a foreground galaxy background source bent all the way around into a circle. Einstein had said in 1936 there was no hope of observing this phenomenon. MG1131 plus 0456 was observed in 1988. Sit with that sequence for a moment. 1936, Einstein publishes the geometry and says it can never be seen. 1937, Zwicky says it will be seen everywhere, especially in clusters, and will be extraordinarily useful. 1979, the first confirmed lens, a double quasar confirmed by identical spectra. 1985, the Einstein cross, 4 images of one quasar. 1987 and 1988, giant arcs in clusters, the Dragon of Hubble 370, confirmed as a background galaxy. 1988, the first complete Einstein ring in radio waves. Everything in this sequence happens between 52 and 48 years after Einstein dismissed the possibility. Almost all of it vindicates Zwicky in ways that are so direct they feel deliberate. Though of course the universe is not deliberate, it simply is what it is, and we were simply slow to look. There is something worth noticing about the pace of confirmation here. These detections did not come in a single dramatic year of revelation. They came one by one, across more than a decade, each one requiring someone to look at something that didn't quite fit, take a spectrum, argue about it for a while, and eventually realize they were looking at a fold in the geometry of space. Science is rarely the moment of discovery. It is mostly the long, careful work of recognition, of understanding what you are already seeing. The twin quasar sat in the data before Walsh and Carswell and Wayman understood what it was. The Dragon arc curved through the images of Able 370 before anyone knew what a dragon it was. The geometry was always there, the eyes took time, and by 1988 all the fundamental forms had been seen. The double image, the quadruple cross, the giant arc, the complete ring. The beastry of gravitational lensing was essentially complete in its basic types. And what remained was to understand what each type was good for, what each could tell you that no other instrument could. Which is where the story begins to get very deep, very quickly, and very useful. But we are not there yet. Rest a moment here, in 1988, with the Dragon arc freshly confirmed and the first radio ring just measured. The field is young and slightly stunned by what it has found. Nobody expected the sky to be this full of bends. Nobody expected the effect Einstein dismissed to be sitting in cluster after cluster, waiting for someone to take a spectrum and realize what they were looking at. The universe was ahead of the theory, not the equations. The equations were right all along, but the human imagination of what the equations implied, of where in the sky to look and what you would find when you looked there, was perpetually behind. Zwicky saw it. Zwicky always saw it. But one prophet in a generation is not usually enough to change a field's direction. What changes a field's direction is data, and the data, by 1988, was beginning to arrive. Let your breath slow a little. There is no hurry here. The arcs in Able 370 are not going anywhere. The dragon has been curving there for billions of years, bending through the cluster's gravity, and it will be curving there for billions more. The universe is very patient about this kind of thing. It put the lenses in place long before there were eyes to use them, and it did not rush. It simply waited, the way the dark waits, with a kind of absolute, unhurried availability. What we have covered in this long, gentle arc of the story is the distance between a man saying no and the universe saying yes. Between a paper published reluctantly in 1936, a short mathematical note for an amateur who would not stop asking, and a radio ring confirmed in 1988, and a blue dragon identified in a cluster of galaxies that had been stretching that arc for longer than our species has existed. Between Einstein's doubt and Zwicky's prophecy, and the long decades in which telescopes slowly grew sharp enough to see what both men, in their different ways, had already described. The mechanism was always the same. Mass curves the road that light travels, not as a force, not as a hand reaching out and grabbing, but as a shape pressed into the fabric of space by weight, the way a heavy stone pressed into still water sends circular ripples outward and downward, changing the surface around it. Light has no choice but to follow the shape of the space it moves through, the same way water has no choice but to flow downhill. There is no pulling. There is only the landscape. And the landscape of a galaxy cluster is not subtle. A cluster carries the mass of hundreds of galaxies, each galaxy carrying hundreds of billions of stars, plus the gas between those galaxies, plus, as we are about to come to, something else. Something that outweighs all of those visible things combined. Something that produces no light at all, but shows up unmistakably in the curving of every arc, the bending of every ring, the geometry of every lensed image we have ever taken. The something that Zwicky named in German in 1933 when he looked at the Coma cluster and did the arithmetic and found it didn't add up. The something the Dragon of Abel 370 was drawing all along had we known how to read the curves. We will come to it soon, but let the detections of the 1980s settle first, the way things settle at this hour, softly and without urgency. The twin quasar, the Einstein cross, the dragon, the first ring, the universe showing us, one image at a time, that Einstein was wrong about what he had found. Not about the mathematics, never about the mathematics, but about whether there was hope. There was always hope. There was light, bending, all the way from the beginning of things, and there were clusters holding it in great curving arms, and there were eventually instruments sharp enough to catch what was bent, and eventually minds patient enough to understand what the bending meant. Hope was never the question. Time was the question, and distance, and the courage to point a telescope at a place where the geometry of space had arranged something more extraordinary than anyone had dared to ask for. So here we are, quietly, at the edge of what the first generation of lensing astronomers saw. The forms are in hand, the double, the cross, the arc, the ring. The principle is confirmed. Mass bends light into images, and the images, if you know how to read them, tell you about the mass, not the glowing mass, the total mass, including the part that does not glow at all, including the dragon that does the bending, while remaining invisible to every instrument we have ever built. Let the darkness settle around that thought. Let the 1988 ring, that first complete radio halo captured by antennas in the New Mexico desert, drift through your mind without needing to be anything more than what it is. A circle of radio light. A background source bent all the way around a foreground galaxy. The thing Einstein said could not be seen. The story is going somewhere richer still. But we are not in a hurry. We are here, in the half-dark, watching the arcs curve, watching the rings close. Following the light down every bent road the universe has laid out for us, one slow step at a time, together, unhurried, through the quiet of a very deep night. Now hold that picture in your mind for a moment. One galaxy, somewhere far behind the cluster, sending its light outward in every direction the way a candle sends warmth into a cold room. The light travels, it reaches the cluster, and there the road bends, not once, but many ways at once, like a river that finds multiple channels around a large stone lying in its bed. Several streams of light from that one distant galaxy find their way around the massive foreground cluster and arrive at us along different curved paths. And so, when we look at the photograph, we do not see one galaxy. We see 4, or sometimes 2, or 5. Occasionally more. The same galaxy, the same object, printed onto the sky in multiple copies because its light took multiple routes to reach your eye. This is not an error in the telescope. This is not noise, or a glitch in the imaging software, or some artifact of how the data was processed on a server farm in Baltimore, or Munich, or Pasadena. This is the geometry of the universe, doing something it is perfectly entitled to do. something that follows without exception from the same principle that explained the 1.75 arcsecond wobble in Eddington's eclipse plates. Mass curves the road, and if the road curves, a single traveller can take more than one path and arrive at the same destination. Picture the galaxy behind the cluster as a lamppost standing in a fog. If you look at it straight on, in open air, you see one lamppost in one place. But put a large, curved piece of glass between you and the lamppost, not a flat pane, but something thick in the middle and thinner at the edges, like an old-fashioned magnifying lens, and the light bends. Suddenly you might see the lamppost doubled. Or, if the alignment is just right, you see it ringed in a circle all around the glass. The galaxy cluster is doing the same thing, except the glass is not glass at all. It is the curved geometry of space itself, shaped by everything the cluster contains, every star in every galaxy of the cluster, every wisp of hot gas between them, and all the invisible dark matter woven through the whole structure, binding it together, contributing its mass, its gravitational weight, to the bending without emitting so much as a photon of its own. The multiple images form because there are multiple paths that light can travel around the lens and still reach the observer. Think of it like water flowing around a boulder in a stream. Some water goes around the left side, some goes around the right. Both streams eventually rejoin downstream, arriving at the same point. The water molecules that went left and the water molecules that went right all come from the same upstream source. They are not different water, just water that took different routes. Photons of light do the same thing around a gravitational lens. A photon that skirts the left side of the cluster and a photon that skirts the right side of the cluster both originate from the same background galaxy. They depart that galaxy at roughly the same time. They travel the universe for billions of years along paths that curve in opposite directions around the cluster's mass. And then both arrive at the Hubble Space Telescope's mirror or the JWST's golden segments or a ground-based observatory's detector, arriving from slightly different directions, which means they appear to come from slightly different places in the sky. We interpret each direction as a separate object. So the same galaxy reads as two galaxies, or four, or five, depending on how many paths the geometry allows. Why four, and not five? This is a delightful question, and the answer lives in a theorem of lens optics that astronomers call the odd number theorem. The mathematics of gravitational lensing, when applied to what physicists call a transparent lens, one where the mass is distributed in space and light can pass through it, predicts that the number of images produced is always odd. One path, or three paths, or five, always odd. This is not an approximation or a limit of our models. It is a hard mathematical result built into the structure of the equations, an odd number of images every time for a transparent lens. And yet when we look at the Einstein cross, we count 4 images arranged around the central galaxy, not 5. 4, which is even. The theorem seems to be broken. It is not broken. What the theorem says is that 5 images should form, but one of them, the 5th, which would appear right at the geometric center of the lens, is almost always squashed, magnified in one direction but compressed in another so that its overall brightness is very low. And in most cases, that 5th image happens to land almost exactly behind the dense, bright core of the lensing galaxy itself. The galaxy's own glare drowns it out. It is there in principle, geometrically mandated by the mathematics, but buried under a blaze of foreground starlight that makes it invisible in practice. So we count 4 and call it a quadruple image, and the theorem survives intact. 5 images form, 1 hides, 4 appear. The odd number is real. The even count is a trick of concealment. This matters for more than tidiness. The fact that one image is always hidden near the center and that its brightness depends sensitively on the mass distribution in the very heart of the lens means that finding that central image or measuring its properties precisely when it does peek out is a way of probing the density structure of the foreground galaxy or cluster at its core. The hidden image carries information, like a letter sealed inside an envelope that is itself stuck to the outside of a package. It tells you something about the container if you know how to find it. But the multiple images do something else, something that sits at the heart of how gravitational lensing has become not just a curiosity, but a working instrument of science. Each image forms in a specific position on the sky, and the exact positions, the angular distances between images, the curvature of arcs, the radius of a complete ring are direct reflections of the mass distribution in the lens. The geometry of the images is a shadow cast by the mass, and that mass includes everything: the glowing stars, the hot diffuse gas, and all the dark matter threading through the structure. Light does not know what kind of matter bent it. It responds to mass, total and complete, glowing or silent, visible or hidden. This is worth pausing on, because it is one of those ideas that seems simple on the surface but has a depth that keeps opening. When you hold a transparent piece of glass in front of a candle, the glass bends the light. The bending depends on the glass's shape, how thick it is, how curved. If you measured the bending precisely, you could infer the shape of the glass, even if the glass were invisible. You would be learning the shape of something you cannot see by watching what it does to something you can. A galaxy cluster does the same thing to light passing through it, except the shape you are inferring is not glass geometry, but the three-dimensional distribution of mass in space. Measure the images, fit a mass model, extract the mass, and there, implicit in the positions of glowing arcs on a photograph, is the full gravitational fingerprint of a structure vast beyond easy imagining, including the parts that no camera and no spectrograph and no X-ray telescope and no radio dish would ever detect on its own. Now, the gravitational lens has 3 modes, 3 distinct registers in which it operates, each useful for a different purpose, each working by the same underlying mechanism but at different scales and different strengths of alignment. Astronomers call them strong lensing, weak lensing, and microlensing, and it is worth letting each one settle gently into your understanding. Strong lensing is the dramatic one, the kind that produces arcs and rings and multiple images that are unmistakably strange even in a casual glance at a photograph. It requires near-perfect alignment. The background source, the foreground lens, and the observer must be arranged so that the light passes close to the densest part of the lens. When the alignment is perfect, or nearly so, you get a complete Einstein ring, that haunting circle of light that Einstein himself calculated in 1936 and immediately declared impossible to observe. When the alignment is slightly off, the ring breaks into arcs, longer or shorter depending on how far off the alignment is. Strong lensing is rare because near-perfect alignment is rare, but the universe is large, and the sky is deep, and there are enough galaxies behind enough massive foreground structures that if you look carefully at a rich cluster, you almost always find arcs, sometimes many. The Hubble image of the cluster SMACS 0723, released on the 11th of July 2022 as the James Webb Space Telescope's first full-color science image, shows so many arcs woven through the frame, thin slivers of light curving around the cluster's core, that the first impression is almost one of decoration, as if someone had drawn crescents of light on a dark canvas purely for aesthetic reasons. They were not drawn. They grew there from the structure of space. Weak lensing is quieter, almost inaudible by comparison. Where strong lensing shouts, unmistakable arcs, obvious multiple images, complete rings, weak lensing whispers. A background galaxy affected by weak lensing is not dramatically distorted. It is only slightly stretched, its circular shape gently elongated by perhaps 1%. 1%. If you looked at a single weakly lensed galaxy, you would not know it had been lensed at all. It would look like a slightly elliptical galaxy, and the universe is full of slightly elliptical galaxies that are simply shaped that way, with no lensing involved. You cannot read weak lensing in a single object. But here is the beautiful statistical lever. If the lensing makes every galaxy in a patch of sky slightly elongated in the same direction, all pointing the same way, all subtly aligned, that coherence is a signal. A field of galaxies has no preferred direction on its own. Galaxies point every which way, randomly, because their intrinsic shapes have nothing to do with each other. If you find that many galaxies in a region are stretched consistently in one direction, something is making that happen. Something between us and those galaxies has gently distorted the paths of their light in a coherent, systematic way. That something is the mass of whatever lies in the foreground. By measuring the coherent, faint alignment of thousands or millions of galaxy shapes across large areas of sky, a signal so subtle it is called cosmic shear. The faint shiver the universe induces in the apparent forms of the galaxies behind it, astronomers can map the total mass of foreground structures. Not just the visible parts. All of it. This is the engine behind the great weak lensing surveys, the Dark Energy Survey, which mapped hundreds of millions of galaxies across a large swath of the southern sky. The Kilo Degree Survey and the Hypersuprime Cam Survey, each building a statistical picture of how mass is distributed across cosmic scales, and now the Euclid mission, launched by the European Space Agency and the Vera C. Rubin Observatory in Chile, whose legacy survey of space and time, the ELST, will map the visible sky with a camera the size of a small car, accumulating images of billions of galaxies over a decade, all of them hunting the cosmic shear signal, all of them measuring the faint 1% stretching of shapes so that the dark scaffolding of the universe, the web of dark matter that holds galaxies in filaments and clusters, the invisible skeleton upon which all visible structure hangs, can be sketched, statistically, for the first time. It is a strange kind of cartography. You are mapping something that emits no light, using as your pen the shapes of things billions of light years away. The map is probabilistic and fuzzy, not the sharp rendering you would get from a direct photograph. But it is real. It traces real structures, and it is, in an important sense, the only map of the dark universe we have. Microlensing is the third mode, and it is the most personal, if you can call a cosmological phenomenon personal. Where strong lensing involves clusters or entire galaxies bending the light of other galaxies, and where weak lensing accumulates tiny effects over millions of objects, microlensing is the story of a single mass, a single star, or a lonely planet, or a black hole no bigger than a city. drifting across the line of sight to a distant background star. When that happens, the background star briefly brightens, not because it has changed, not because of any process in the star itself, but because the passing mass has briefly bent more of the star's light toward the observer, the way a glass marble rolled across a lit table briefly intensifies the light you see through its center. The brightening lasts hours or days or weeks, depending on how fast the lensing mass is moving and how massive it is. Then it fades back to normal. Microlensing is its own deep science. It has found planets orbiting distant stars, has hinted at the presence of free-floating planetary mass objects drifting through the galaxy without any parent star, and has placed constraints on what dark matter cannot be by watching millions of background stars for microlensing events. But it lives at a different scale from cluster lensing, and it is mentioned here mainly to complete the family portrait. These three modes, strong, weak, micro, are not different phenomena. They are the same phenomenon viewed through different lenses of scale. One principle: mass curves spacetime. Light follows. The dramatic arcs of a galaxy cluster, the barely perceptible stretching of a galaxy's ellipticity, and the brief brightening of a single distant star are all expressions of the same mathematical truth, operating at distances and masses that span 15 orders of magnitude. What ties them together is a quantity called the Einstein radius. And the Einstein radius is worth understanding because it is the bridge between the observed geometry of a lens and the physical quantity the lens is actually measuring: mass. The Einstein radius is, in the simplest terms, the angular size of the ring that forms when a source, lens, and observer are in perfect alignment. When you have a complete Einstein ring, that full circle of light, its radius on the sky is the Einstein radius. When you have arcs and multiple images instead of a full ring, the Einstein radius is still there, implicit in the geometry, describing the scale at which the strong lensing effects are occurring. It tells you how large the lane of strong lensing is around the central mass. And here is the key: the Einstein radius scales with the square root of the lens mass. Double the mass of the lens, and the Einstein radius grows by the square root of 2, about 40%. Quadruple the mass, and the radius doubles. The ring is, in a very direct physical sense, a measuring instrument. Its size on the sky encodes the mass of everything inside it. In a relationship so clean and direct that you can literally look at a ring, measure its angular radius with your ruler, and from that number derive the mass of the foreground lens. No spectrograph needed. No assumption about how the stars are moving. Just geometry and Einstein's equations and the radius of a ring of light. This weighing works for dark matter too. In fact, the weighing works especially well for dark matter, because dark matter is the dominant mass component in most galaxy clusters. When you measure the Einstein radius of a giant arc system in a cluster, you are not just weighing the stars and gas you can see, you are weighing the whole gravitational structure, the total budget of mass that produces the lensing geometry you are observing. The dark matter is inside the measurement. It cannot hide from it. A gravitational lens does not care whether its mass is shining or silent. It responds to all of it, and the ring radius reflects all of it. So what are the actual numbers? In a typical galaxy cluster, the stars in the member galaxies account for only a few % of the total mass. The hot gas, the intergalactic plasma that fills the cluster at temperatures of tens of millions of degrees and glows brightly in X-ray light, adds another 10 to 15%. And the rest, the remaining 85% or so of the mass that the lensing geometry requires to explain the arcs and rings, is dark matter, not slightly more than expected. Not a small correction, about 85%. Dark matter outweighs everything else in a galaxy cluster by a ratio of roughly 6-1. And those numbers, the fraction of the universe that is ordinary matter versus dark energy, fit into a picture that has been confirmed across many independent lines of evidence. Ordinary matter, everything you have ever touched or seen or tasted or built, constitutes about 5% of the universe's total energy content. Dark matter accounts for roughly 27%. And dark energy, the name given to whatever is driving the universe's expansion to accelerate, makes up about 68%. Of all the matter in the universe, taking just the matter component and ignoring dark energy, approximately 85% is dark matter. 15% is ordinary. We are the footnote. And that is where the light is most honest. A gravitational lens does not discriminate, it bends to the full mass, including the 85% that emits nothing. When you look at the arcs in a cluster photograph, you are not just seeing a pretty optical effect, you are looking at a map. The arcs trace the gravitational potential of the whole structure, glowing matter and dark alike. The curvature of each arc, the position of each multiple image, the radius of each ring, all of these are encoded with information about where the mass is and how much of it there is, dark matter included. You cannot see the dark matter, but you can read its handwriting in the light. For most of the 20th century, this was an elegant idea that was genuinely difficult to prove. The evidence for dark matter was strong, but indirect. Fritz Zwicky had inferred in 1933 that the galaxies of the Coma cluster were moving too fast to be held together by their visible mass alone. He coined the term Dunkel Materie, dark matter, and the name stuck. But the concept remained controversial for decades. Measurements of the rotation of spiral galaxies in the 1970s by Vera Rubin and her colleagues showed that stars in the outer reaches of galaxies were orbiting too fast for the visible mass to account for, again implying an unseen mass component. These were kinematic arguments from motion. They were powerful, but they could always be greeted with the counter-argument that perhaps our theory of gravity was slightly wrong at large scales, that the equations might need a small correction, that dark matter might be an artifact of a mistaken model rather than a real substance filling the universe. Then came the bullet cluster. The bullet cluster is officially catalogued as 1E 0657558. It is not a single cluster. It is the aftermath of a collision. Two galaxy clusters that passed through each other at enormous speed, somewhere around 100 million years ago as we reckon time, and are now flying apart on the other side of the impact. Astronomers David Clow and colleagues published their analysis in 2006. And it has remained one of the most discussed results in cosmology ever since. Not because it was mathematically complex, because what it showed was almost brutally simple. When the two clusters collided, their member galaxies, the actual galaxies with all their stars, mostly passed through each other without significant interaction. The way two swarms of bees might fly through each other with only occasional collisions, because the individual bees are so tiny relative to the space between them. The distances between stars in galaxies are so vast that when two galaxies encounter each other, the stars generally do not actually hit. They interact gravitationally, they distort each other, they sometimes get flung into new orbits. But direct stellar collisions are rare. So the galaxies went through. The hot gas of the two clusters did not go through. Hot gas is not a swarm of discrete particles separated by enormous distances. It is a continuous medium, a plasma filling the space between the galaxies, and when two clouds of hot plasma slam into each other, they interact. They slow down. They create pressure waves. They heat up. They get stuck in the middle, even as the galaxies that contained them continue past. So after the collision, the hot gas, which was the largest component of visible matter in each cluster, more massive than all the stars combined, was found concentrated in a region between the two galaxy groups, while the galaxies themselves had already travelled well beyond it on either side. Now, the key. The hot gas contains most of the visible mass of the cluster, more mass than the stars. If dark matter is simply a mistake in our gravity model, if what we are calling dark matter is actually just ordinary matter that we have miscalculated or misunderstood, then the mass should follow the hot gas, because the hot gas is where most of the visible mass is. The gravitational effects, the lensing, should be centered on the gas. They were not. The weak lensing mass map, the map of total mass derived from the coherent stretching of background galaxies, showed the mass concentrated around the two separated galaxy groups. Not in the center, not where the gas was. The mass had travelled with the galaxies right through the collision, as if it had simply ignored the impact. Because dark matter, unlike hot gas, does not interact electromagnetically. It does not slow down when it passes through ordinary matter. It barely interacts with anything except through gravity. So the dark matter of each cluster passed through the dark matter of the other cluster, essentially unimpeded, just as the galaxies did. And afterward, the dark matter, which constitutes approximately 85% of the cluster mass, was found on the sides with the galaxies, while the hot gas, most of the visible mass, was trapped in the middle. The mass and the visible matter had been physically separated. They were in different places. You could point at the gas with an X-ray telescope and say there is most of the ordinary matter. And you could point at a different part of the sky, separated by a real measurable angular distance, and say there is where the lensing maps say the mass is. Two instruments, two measurements, two different answers about where the matter is. And both answers were right, because they were measuring different things. This is why the bullet cluster became, and remains, such a celebrated result. The alternative gravity hypotheses, the frameworks that tried to explain the anomalous motions of galaxies and clusters by modifying the equations of gravity rather than by invoking unseen matter, generally predict that the mass follows the visible baryons. Modify gravity, and you do not separate mass from matter. The gravitational effects are always where the ordinary matter is, because in those frameworks there is no independent dark matter to move elsewhere. The bullet cluster shows that the mass is not where the ordinary matter is. The two are physically separated by the mechanics of a collision. To maintain that there is no dark matter, you need a theory of modified gravity that can somehow make the gravitational mass of a cluster trail its galaxies through a collision instead of following the gas, which is where most of the ordinary matter sits. That is a very difficult thing to arrange without effectively reintroducing a dark matter-like substance under a different name. The scientific community has not declared the case for dark matter proven beyond all doubt. That is not how science works, and there remain theorists working seriously on modified gravity alternatives, and they deserve a sentence of honest acknowledgement. But the bullet cluster strongly disfavors those alternatives. It is the closest thing cosmology has to a smoking gun, a situation where the predictions of dark matter and the predictions of modified gravity diverge, and where observations clearly favor one over the other. As Clough and colleagues wrote in their 2006 paper, this represents a direct empirical proof of the existence of dark matter in the cluster, or at minimum, of a dominant non-baryonic mass component that behaves the way dark matter is predicted to behave. The gravitational lens drew the map. The map showed the dark matter, and the dark matter was somewhere other than the gas. Let that image rest quietly. Two clouds of hot plasma, millions of light-years across, caught in the frozen moment of their aftermath. Tangled and brilliant in X-rays in the space between the separated galaxy groups, while the dark matter, invisible and interpenetrating, has sailed on ahead as if nothing happened. On one side, the glowing gas, hot and luminous, stuck. On the other sides, the galaxies and the great invisible envelopes of dark matter surrounding them, already pulling away. A collision that separated light from shadow. A photograph that shows, in the most literal and spatial sense, that the dark matter is real, that it occupies real volume in real space, that it has passed through the ordinary universe like wind through a screen door, carrying the mass that the arcs and the ring radii and the Einstein equations say must be there. We have spent time with the dramatic center of this story, the arcs, the rings, the bullet cluster, the Einstein radius as a weighing instrument, and the picture is becoming whole. It begins, always, with the same simple truth: mass curves spacetime, and light follows the curve. From that single line, everything else flows. Multiple images, because light finds multiple curved roads around a massive lens. Rings when the alignment is perfect, arcs when it is imperfect, and the radius of the ring encoding the mass of the lens directly. 3 flavors of lensing: strong, weak, micro, each a different window on the same underlying geometry, from the dramatic arcs of clusters down to the brief brightening of a single background star. And threading through all of it, doing most of the bending while remaining utterly invisible, the dark matter that outweighs everything we can see by a factor of roughly 6 to 1. The arcs in a cluster photograph are not decoration, they are not noise, they are data, and they are among the richest data the universe sends us. Each arc is a question about the mass that bent it, about the galaxy that was stretched into it, about the distance that the light has travelled and the time it has spent crossing the intervening space. And each arc is simultaneously an answer, if you know the language, if you have the tools to decode the curvature into a mass distribution, the position into a distance, the achromatic appearance across all wavelengths into a confirmation that yes, this is lensing, this is real. The light you are seeing has genuinely been redirected by the geometry of space itself. There is something that feels, in the very best sense, collaborative about it. The universe has arranged these alignments on its own schedule, indifferent to us, according to physical laws that were operating long before anything on this planet was alive to wonder about them. And then we, the small curious creatures on the rocky inner planet of an ordinary star in the outer arm of a middling galaxy, built instruments and mathematics and launched telescopes into orbit above the distorting atmosphere and pointed them at clusters and found the arcs. And we learned to read them. And in the reading, we have begun to draw a map of something that cannot be seen, not seen in any direct sense, not detected by any instrument that senses photons, not weighed by any scale that measures ordinary matter. A map of the dark infrastructure upon which everything we have ever known is organized. The universe has, in a sense, provided us with a way to see what it has hidden. It did not hide the dark matter in defiance of curiosity. It hid it in the nature of things, in the silence of matter that does not couple to light. And then it left a loophole. The same mass that does not glow still curves space. And curved space writes its signature on the light that passes through it. The light carries the message, and the message says, "There is more here than you can see. Much more. And here, precisely, is where it is." That is the gift of the lens, not just a beautiful image, not just a ring of light for wonder's sake, though the wonder is real and is not nothing. The gift is a window into the unseen, a way of reading the invisible, a method that turns the structure of spacetime itself into an instrument of measurement. And the clusters, those enormous concentrations of galaxies and gas and dark matter, sitting at their cosmological distances, bending the light of everything behind them, are the best lenses the universe has provided. Not the smallest, not the most precise, but the largest, and in some ways the most generous, a lens light years across, capable of magnifying the light of a galaxy from the universe's first few 100 million years into something bright enough to fall on a telescope mirror and leave its trace in data. Which is where the story is going next. The clusters as tools, as intentional instruments, as the targets of deliberate observing programs designed to look through them rather than at them. To use the universe's own optics to see what lies beyond the reach of anything we could build. The arcs are still curving in the quiet dark. The dark matter is still there, invisible and vast, holding the clusters together, writing its signature in the light. And somewhere behind all of it, much farther away, the first galaxies that ever formed are waiting to be read, waiting to be seen, lit by the lensing of the great clusters in the foreground, delivered into our instruments by the same mass curve spacetime truth that Eddington confirmed in 1919, and Zwicky prophesied in 1937, and Einstein himself doubted in 1936. The night holds all of it quietly. You do not need to reach for any of it. Let it come to you, the way starlight comes, at its own pace, on its own curved roads, through the slow, unbounded dark, arriving gently, settling without urgency into the instrument of your attention, unhurried, complete. So there came a moment when astronomers stopped, simply noticing the arcs, and started planning around them. The shift sounds small. It was not small. It was the difference between finding a useful tool by accident and deciding deliberately to build your most ambitious observations around the fact of its existence. The clusters were not just interesting objects anymore. They were instruments. The universe had placed them there, massive and gravitationally powerful, and the question became, what could you see? If you looked through them instead of at them? The answer required patience. It required years of committee decisions and telescope scheduling and the slow accumulation of evidence that looking through a cluster rather than past it was worth the observing time. But eventually, the case became undeniable. If you wanted to see the faintest, most distant galaxies, the ones that formed when the universe was still in its first few 100 million years, when the first stars were only just beginning to burn, when the light we would eventually receive had not yet begun its long journey, you needed magnification that no human-built instrument could provide. And there, already waiting, were the clusters. The Hubble Space Telescope had shown this could work, in glimpses, for years. Individual arcs had been traced back to sources at enormous distances. Lensed galaxies had been confirmed at redshifts that corresponded to light ages that strained the imagination. but a structured, deliberate program, pointing Hubble at the most massive clusters specifically to use them as magnifying glasses. Spending hundreds of orbits staring through them into the deeper dark, that took until 2013 to formally begin. The Hubble Frontier Fields program chose 6 clusters. 6 of the most massive, most gravitationally powerful accumulations of matter known to astronomy, selected precisely because their lensing geometry was favorable, their mass distributions well modeled, and their placement in the sky convenient for deep observation. The program ran from 2013 through 2017, spending approximately 840 orbits of Hubble time, which is an enormous allocation, a statement of institutional seriousness. The 6 clusters were Abell 2744, MAX J0416, MAX J0717, MAX J0149, Abell 370 and Abell Cento 63. And alongside each cluster image, Hubble also captured a parallel deep field nearby, a blank patch of sky observed at the same depth, so that astronomers could compare what lensing revealed against what the unaided view could find. Abell 2744 carries a nickname that tells you something about its character, Pandora's Cluster. It earned that name before the Frontier Fields program, when earlier observations revealed that it appeared to be the aftermath of several clusters colliding simultaneously, a chaotic, violent merging that had scattered its mass unevenly, created multiple concentrations of dark matter, and produced a complex lensing geometry with arcs running in various directions across the image. Where a single, spherically symmetric cluster produces smooth, regular arcs, Pandora's cluster produces a more complicated pattern, like light bent through a lens that has been slightly warped and twisted. The galaxies behind it appear stretched and curved in ways that require detailed modeling to untangle. But the complexity is not a defect. A complex mass distribution produces a complex lens, and a complex lens can magnify light from multiple directions and distances simultaneously, offering a richer view of the background universe than a simpler cluster might. MAX J0416 sits in the constellation Eridannus, and it too is a merging system, 2 clusters in the process of falling together, their combined mass producing a lensing field of considerable power. MAX J1149 is where one of the program's most remarkable discoveries eventually emerged, though that story belongs to the time delay thread and waits a little ahead. Abell 370 is the old familiar one, home to the Dragon arc, the first giant arc ever confirmed spectroscopically, still one of the most studied lensing configurations in the sky. Abell N063 rounds out the 6 with a clean, massive lensing geometry that has since yielded some of the deepest images of background galaxies taken with Hubble. The program produced images of extraordinary depth. In each cluster field, hundreds of arcs were catalogued, their redshifts measured where possible, their source galaxies identified and characterized. The Frontier Fields images extended Hubble's view of the early universe by what was effectively the equivalent of adding another mirror several times the telescope's actual diameter, not through engineering, but through the gravitational generosity of the clusters in the foreground. Objects that would have been completely invisible in a blank field, too faint for Hubble's mirror to collect enough photons to detect, appeared as faint curved smears in the cluster fields, magnified into detectability by factors of 10, 20, sometimes 50, or more along the critical curves where the lensing geometry was most favorable. One of those objects is a galaxy designated MAX 1149 JD1, found behind the cluster MAX J1149. Its light, as best as astronomers can reconstruct from its spectrum and the lensing model, left its source when the universe was approximately 500 million years old. That means looking at Max 1149 JD1 is looking back across roughly 13.25 billion years of cosmic history, to a time when the universe was only about a 27th of its present age. At that epoch, galaxies were only just assembling. The first generations of stars had formed perhaps a few 100 million years earlier. The light from Max 1149 JD1 carries within it the record of a galaxy in an early, formative state, small, irregular, intensely active with star formation, burning through its gas at rates that modern, mature galaxies like our own Milky Way could not sustain. Without the lensing of Max J1149, that galaxy would be invisible. The photons reaching us from it are so few, and their energy spread so thin by the expansion of the universe, that no telescope we have built could accumulate enough signal from the direct, unmagnified source to detect it at all. The cluster made it visible. There is a useful distinction to hold here, because it matters for understanding what lensing actually achieves. The most distant galaxies ever detected are not necessarily the ones found through lensing. The deepest reaches of the observable universe, in terms of raw distance, are sometimes found in unlensed deep fields, where Hubble and then JWST have stared at blank patches of sky for hundreds of hours and found objects at extraordinary redshifts simply by the power of the instruments themselves. The current record holder, as of recent years, is a galaxy designated JADES GS-Z14 Eero, with a redshift of approximately 14.32, which corresponds to light that left its source only about 290 million years after the Big Bang. That galaxy was found not through lensing, but in a blank deep field observed by JWST, the James Webb Space Telescope, using the pure unassisted sensitivity of its mirrors and detectors. What lensing adds is not necessarily greater distance, but greater brightness. It takes objects that are simply too faint to see, not because they are at the absolute limit of how far away we can look, but because they are intrinsically dim or small or in a configuration where their light has spread too thin, and it concentrates that light, amplifies it, brings it across the threshold of detectability. Lensing is the tool for the faint and the small. The raw distance record goes to the deep fields. But some of the most scientifically valuable early universe objects, the ones that can be studied in enough detail to yield spectra and chemical compositions and star formation rates, are the ones that lensing has made bright enough to examine closely. Earendel, that single star from 12.9 billion years ago in the sunrise arc behind cluster WHL 013708, is the extreme case of this. It is not the most distant object ever detected. But it is the most distant individual star, a single point source rather than a galaxy, and it exists above the threshold of detectability only because the cluster magnified it by a factor estimated in the thousands. A factor so large that it strains the models to fully account for. Achievable only because Earendel sits almost precisely on the critical curve, that narrow seam in the sky where the lensing magnification approaches its maximum. The cluster did not make Earendel visible in the ordinary sense. It performed something closer to a miracle of physics, concentrating the light of a star that by all ordinary reckoning should have been unreachable for any instrument that humanity will build in any foreseeable future. JWST arrived into this landscape in 2022, and its first scientific deep field image was not chosen at random. On July 11th of that year, the telescope released its first full-color image to the public, and the subject was SMAC 0723, a galaxy cluster at a moderate cosmological distance, selected in part because its lensing geometry was well understood, and in part because it would demonstrate immediately and visibly what the new telescope could do. The image was dense with arcs. Thin, curved smears of light ran across the field in multiple directions, each one a background galaxy or group of galaxies bent and stretched by the cluster's mass. The colors in the image encoded real information, the spectral energy distributions of objects at various distances, their light stretched by the expansion of the universe into the infrared wavelengths where JWST detectors are most sensitive. Some of the arcs in that first image came from galaxies that formed when the universe was only a few % of its current age. JWST was built with lensing in mind, in the same sense that Hubble's frontier fields were. The telescope's infrared sensitivity makes it ideal for observing the most distant galaxies, whose light has been redshifted out of the visible spectrum entirely into wavelengths that Hubble cannot easily see. But that same infrared sensitivity also makes JWST extraordinarily effective at studying lensed sources, because the clusters doing the lensing can be observed simultaneously with the background galaxies behind them. And the combination of lensing magnification and JWST's instrumental sensitivity pushes the observable frontier further than either could alone. Programs targeting lensing clusters have been among JWST's most productive in terms of identifying and characterizing the earliest galaxies ever studied. The universe has, in this sense, been quite deliberate in its placement of tools. The clusters are not uniformly distributed. They grow in the dense nodes and filaments of the cosmic web, in the places where matter accumulated most efficiently over billions of years. Some of them happen to sit along lines of sight toward regions of the sky that have been extensively studied for other reasons, or that contain remarkable background sources. This is partly chance and partly selection effect. Astronomers look at the clusters that are most useful to them, and over decades of observation, the most productive sightlines have been identified and returned to repeatedly. The consequence is that a handful of clusters, Abell 2744, Max J1149, Abell 370, a few others, have become known in extraordinary detail, their mass distributions modelled to high precision, their lensing geometry mapped across the full field, their magnification as a function of position calculated and tabulated so that any background source can have its intrinsic brightness reconstructed from its observed brightness. And this brings the story to its third great use, the one that is perhaps the least obvious but in some ways the most profound. Not magnification, not dark matter mapping, but time. The multiple images of a lensed source are not just multiple images. They are the same source viewed along different paths, and those paths have different lengths. Light travelling along a shorter, more direct path arrives before light travelling along a longer, more curved path. The difference can be hours, or days, or weeks, or years, depending on the geometry of the lens and the distances involved. If the source is something that varies in brightness over time, or something that produces a one-time event, you will see that variation or that event appear at different moments in the different images, offset by exactly the travel time difference between the paths. A Norwegian astronomer named Sjur Refsdal understood this in 1964. He was thinking about the physics of the newly discovered quasi-stellar objects, quasars. And he worked out that if a quasar were gravitationally lensed into multiple images, and if you monitored those images over time and measured the brightness variations as they echoed from one image to the other, you could extract from the timing difference a direct measurement of the expansion rate of the universe. This is not an indirect or modelled measurement. It is a geometric measurement rooted in the simple fact that a longer path takes longer to traverse, and the length of the path depends on the geometry of spacetime, which in turn depends on how fast the universe is expanding. Refstal's 1964 paper proposed a method that was, in principle, independent of every other cosmological measurement then available. A way to read the universe's expansion rate from nothing more than the light curves of a lensed source and the geometry of the lens. It took decades to find a system clean enough to use this way. Quasars were monitored. Time delays were measured. The Hubble constant estimates that came from them were tantalizing but carried large uncertainties because the lens models were imprecise and the quasar variability was complex and hard to disentangle from genuine time delay signals. The field advanced slowly, waiting for a better system. In 2014, looking at the cluster max J1149, astronomers found what Refstal had imagined. A supernova, not just any supernova, but one lensed into an Einstein cross, 4 images of the same exploding star arranged around the core of a galaxy within the cluster, with a 5th additional image expected to appear separately via a longer path around the cluster mass itself. The timing and geometry of the system were modelled carefully. The 4 images of the cross had already appeared by the time the discovery was published. The 5th image, the one taking the longer route around the cluster, was predicted to reappear at a specific location in the field, at a specific time, within a range that the models constrained to somewhere in the following year or so. The team named the supernova Refstal in honor of the man who had proposed that exactly this kind of observation was possible in 1964. And then they waited. In December 2015, the predicted image appeared, right where the models said it would be, within the predicted time window. A point of light brightened at the expected location in the cluster field, grew to maximum brightness over the expected timescale, and faded in the way a supernova does. It was supernova Refstal, arriving via its longer path, on schedule, confirming not just that the lens models were correct, but that the entire conceptual edifice, Refstal's 1964 insight, the geometry of spacetime distorted by mass, the predictability of light's travel through that distorted geometry, was sound enough to make and keep a prediction in advance. Astronomy rarely offers pre-registered predictions of this kind. The appearance of supernova Refstal's 5th image is one of the field's cleanest confirmations of a theoretical forecast. The timing data from supernova Refstal and the cluster max J1149 were subsequently used to produce a measurement of the Hubble constant, the number that describes how fast the universe is expanding, expressed in kilometers per second per megaparsec, meaning how many kilometers per second faster a galaxy recedes for every additional 3.26 million light-years of distance. The value derived from the Refstal time delay analysis came to roughly 64 to 66 kilometers per second per megaparsec. This is a number worth pausing on, not because of what it is exactly, but because of where it sits relative to other measurements. There are 2 primary families of Hubble constant measurements. One comes from the early universe, from the pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, and yields values around 67 to 68. The other comes from the local universe, from measuring distances to relatively nearby galaxies using standard candles like Cepheid variable stars and Type I supernovae, and consistently yields higher values, around 72 to 74. This discrepancy, about a 10% difference, which sounds small but is far larger than the measurement uncertainties on either side, is what cosmologists call the Hubble tension, and it has not been resolved. The Refstal measurement sits closer to the early universe values, which is one data point in a complicated ongoing debate. But what matters here is what the technique represents. Time delay cosmology, the method Refstal proposed in 1964, has become a working research program. The same cluster that houses the frontier fields targets, that magnifies the early universe's faintest galaxies, that bends the light of background objects into arcs and rings, that same cluster can be used, with enough patience and careful modeling, to measure the rate at which the whole cosmos is expanding. One object. 3 impossible jobs. Magnifying glass, dark matter map, and cosmic ruler all at once. There is a moment of stillness in thinking about that, a cluster of galaxies, billions of light years away, sitting quietly in the dark, doing physics on a scale that no instrument of human engineering has ever approached, and doing it continuously, without pause, in every direction at once. The arcs are forming and reforming as the background sources move, cosmologically slowly. The time delays are ticking, light taking its various curved paths and arriving in sequence. The dark matter is holding the whole structure together, as it always has, invisible and foundational. The beauty of specific objects, the set pieces, the ones that have become famous in astronomical imagery, captures something of this, even if a single image cannot hold all 3 functions at once. The cosmic horseshoe, officially designated LARG 3757, is one of the most striking examples of a near-complete Einstein ring known. A massive foreground galaxy, one of the largest and most luminous known, sitting at a distance of several billion light-years, has aligned closely enough with a background galaxy to produce a ring that stretches almost completely around it. An Einstein radius of approximately 5 arcseconds, among the largest measured. The ring is not quite closed. It is a horseshoe of bright blue light curving around a large orange elliptical galaxy, the color difference telling the story at a glance. The orange is the old stellar population of the foreground lens. The blue is the younger, more actively star-forming background galaxy, stretched and bent around it. It is a textbook image of strong lensing made real, the geometry that Einstein worked out in 1936, rendered in light that reaches across billions of years. Then there is SPT 041847, sometimes called the Molten Ring, a source galaxy that wraps into an almost perfectly circular ring of light around its foreground lens. The background galaxy in this case is compact enough, and the alignment precise enough that the ring is nearly unbroken. A loop of warm orange-gold light in images from ALMA, the radio and millimeter wave array in Chile's Atacama Desert that is sensitive to the cold gas and dust emission from early galaxies. The molten ring source is a galaxy from the early universe, its light telling the story of star formation and chemical enrichment in the period when galaxies were assembling rapidly. The ring was known before JWST, but subsequent observations added layers of detail, the lens model refined, the source galaxy reconstructed from the stretched arc into something close to its actual appearance. And 2M1310-1714, another near-complete ring, quieter in the astronomical literature but no less real, another place in the sky where an alignment has produced the geometry Einstein doubted would ever be found, a full loop of bent light sitting against the blackness between the stars. Each of these is a place where the universe has solved an alignment problem of extraordinary precision. The background source, the foreground lens, and the observer must be nearly collinear, on a line, or close enough to one that the ring or near ring forms. Given the vast number of galaxies and clusters distributed through the universe, and given that observations now cover large fractions of the sky with sufficient depth to find faint arcs, the number of known lensing systems runs into the thousands. Rings, crosses, arcs, doubles, the sky is populated with them, and surveys designed to find them systematically turn up more with each passing year. This is where the dark matter mapping programs come in, the large-scale surveys that use not the dramatic arcs of strong lensing, but the faint, statistical signal of weak lensing. The coherent, tiny stretching of millions of background galaxies by the large-scale distribution of mass in the foreground universe. Each individual galaxy in a weak lensing survey is stretched by only about 1%. You cannot see it in a single galaxy. The galaxy's own shape uncertainty is far larger than the lensing signal, but average over hundreds of thousands of galaxies in a patch of sky, and the signal emerges from the noise. The background galaxies are preferentially stretched in directions perpendicular to the direction toward the nearest mass concentration, because the tidal component of the gravitational field does the same thing to extended objects that it does to the tides of the oceans. It stretches them along one axis and compresses them along the other. Map this stretch signal statistically across the sky, and you recover a map of the projected mass distribution, dark matter and all, without ever needing to know what dark matter actually is. This technique, called cosmic shear, is the engine of several of the largest survey programs in modern observational cosmology. The Dark Energy Survey, which imaged a large fraction of the southern sky over several years, used weak lensing as one of its primary probes of the universe's matter distribution and the properties of dark energy. The Kilo Degree Survey, the Hypersuprime Cam Survey, each has contributed large catalogues of galaxy shapes, carefully calibrated for the instrumental effects that can mimic or mask a lensing signal, and has extracted dark matter maps covering hundreds or thousands of square degrees of sky. And now, from the 2020s onward, the scale has expanded again. The Euclid satellite, a mission of the European Space Agency launched in 2023, is designed specifically to map weak lensing across roughly a third of the entire sky, measuring the shapes of billions of galaxies with the kind of precision that requires a space-based platform, because the blurring and distortion introduced by Earth's atmosphere would otherwise swamp the tiny lensing signals. Euclid's primary scientific goal is to understand the nature of dark energy, the something that is causing the universe's expansion to accelerate, and weak gravitational lensing is one of its two main tools for doing so. A map of how dark matter is distributed across the universe and how that distribution has changed over cosmic time encodes information about the interplay between gravity and dark energy that can constrain the cosmological models in ways that no other observation can. On the ground, the Vera C. Rubin Observatory in Chile, named for the astronomer who spent decades producing the most compelling observational evidence that dark matter existed, working from the rotation curves of galaxies, is preparing its legacy survey of space and time, known as JWST. Over 10 years, starting in the mid-2020s, the Rubin Observatory will photograph the entire available southern sky repeatedly, building up a data set of unprecedented depth and temporal coverage. Weak lensing science is central to JWST's design, the telescope's camera, the largest astronomical camera ever built. Its mirror optimized for survey speed, its software pipelines designed from the start to handle the data volumes involved, all of it calibrated against the requirement that the shape measurements of billions of galaxies be accurate enough to detect cosmic shear signals at the level of a fraction of a percent, at separations ranging from the scale of individual galaxy clusters to the scale of the observable universe itself. The dark matter, whose existence was first inferred from galaxy rotation curves and galaxy cluster kinematics, whose reality was most dramatically demonstrated by the bullet cluster, is now being mapped with increasing precision and coverage across the sky. Not by looking at it directly, it emits nothing, absorbs nothing, interacts with nothing we can detect except through gravity, but by reading the light of the galaxies behind it, carefully, patiently, over enormous sky areas and enormous galaxy samples, extracting the coherent stretching that the dark matter imposes on the shapes of everything behind it. The pen drawing the invisible is gravity itself, and the medium is light, and the canvas is the sky. There is something that wants to be said now, at the end of all of this. Something about what it means to have spent this time, yours and mine, the quiet time before sleep, sitting with a piece of physics that began as a theoretical calculation about the shape of spacetime, that was confirmed in a field in Africa watching the stars around an eclipsed sun, that was doubted by the man who originated it, that was extended by a contrarian Swiss astronomer who saw further than almost anyone, and that has become, over the decades since its first real detection in 1979, one of the most productive and beautiful tools in the history of astronomy. Einstein in 1936 wrote that there was no hope of observing the Einstein ring. He was thinking small, one star lensing another, an alignment achievable only in geometry, never in practice. The sources too faint and the angles too precise to be found in any sky survey then imaginable. He was not wrong about the difficulty. He was wrong about the scale. What he had not imagined, because the observational technology did not yet exist and the theoretical framework had not yet been extended, was that the universe is full of lenses far more powerful than a single star. That whole clusters of galaxies, with masses hundreds of trillions of times the mass of the Sun, sitting at cosmological distances, aligned by the same random chance that places any two objects along a sightline, would produce the phenomenon he had calculated at a scale so large that it would be impossible to miss, once anyone knew to look. The first ring was found in 1988 using a radio telescope array, its signature a near-complete circle of radio emission from a background source. The alignment close enough that the central image and the ring are both detectable. By then, Zwicky had been dead for 15 years, Eddington had been dead for 40, Einstein had been dead for 33. None of them saw it. But the event they variously predicted, confirmed, extended, and doubted was happening in the sky throughout all those years, as it had been happening for billions of years before any human being existed to care about it. The cluster of galaxies does not know that it is a telescope. The dark matter does not know that it is being mapped. The light does not know that it is being bent. Physics operates without awareness, without intention, without any reference to the minds that eventually learn to read it. What we bring is the reading, the long patience of accumulating observations, the mathematics that connects a measured arc to a mass distribution, the creativity that says, the alignment condition Einstein dismissed as impossible is actually satisfied millions of times across the observable sky, if only you know what you're looking for. The humility to point a telescope at a cluster and say, "I am not trying to understand the cluster today. I am trying to look through it, to use its gravity as my instrument, to read the universe behind it that I would otherwise never see." And then the courage to come back to that data, night after night, program after program, and to find in it things that no one expected. Earendel, a single star 12.5 billion years old, the Einstein cross of supernova Refstal, and then its predicted fifth image arriving on schedule in December 2015, a pre-registered prediction kept by the universe in the way the universe always keeps its promises, by following its own laws without exception, without mercy, without any special provision for the curiosity of the beings who live inside it. A galaxy from 500 million years after the Big Bang, Max 1149 JD1, small and young and burning bright in its youth, brought across the distance threshold by the magnification of a cluster it has never interacted with and never will. The light from all of those objects is still arriving. Right now, as you settle into the particular softness of wherever you are, as the sounds of the night find their natural level and the day releases its hold on your attention, that light is still travelling. Earendel's photons, bent thousands of times brighter by WHL 13708, are still completing their journey. The arcs in SMACS 0723 are still forming, still curving around mass concentrations that include the dark matter doing its quiet gravitational work. The cosmic horseshoe is still a horseshoe of blue light wrapped around an orange galaxy, patient as geometry, unchanged by whether anyone is observing it. And somewhere, along the long filaments of the cosmic web, in clusters we have not yet observed carefully enough to find their best lensing geometries, there are galaxies from the universe's very first 100 million years. Galaxies whose light is bright enough to detect only because a massive cluster happens to sit between them and us, concentrating their signal by a factor of 50, or 100, or more. Waiting, not impatiently. They have already been waiting for 13 billion years, which is a patience beyond the reach of any analogy the human experience offers. The waiting is simply the nature of light in an expanding universe. It travels and arrives when the geometry allows. JWST is looking. Euclid is measuring. The Rubin Observatory is preparing to survey. The programs that Zwicky imagined in 1937, using galaxies as lenses, weighing the invisible, testing the fabric of spacetime with the light of background objects, are now large-scale industrial operations, conducted with instruments of extraordinary sensitivity, producing datasets that will take decades to fully analyze. The dark matter maps that Vera Rubin spent her career arguing were necessary, that lensing would eventually provide, are being assembled from the shapes of billions of galaxies, each contributing its tiny coherent signal to a picture that resolves slowly into the skeleton of the large-scale structure of the universe. The rings are there. The arcs are there. The invisible dark matter is there, writing its signature in light it never touches, felt only as a curvature in the road that the light travels. Einstein said there was no hope of observing this phenomenon. The universe disagreed, and it went on doing the phenomenon regardless, and eventually we built the instruments and the understanding to see it. And what we found when we looked was not just a curiosity, but a tool, a clock, a map, and a window into the universe's earliest chapters, all assembled from the single quiet fact that mass curves spacetime and light follows the curve. You don't need to hold all of that right now. The arcs will still be there in the morning, and the dark matter will still be holding the clusters together. And Earendel will still be there in its sunrise arc, magnified by thousands, the most distant star any human instrument has ever resolved, still crossing the last few light years of its journey toward the mirror of a telescope built by people who had no way of knowing, when they started designing it, that it would one day fall on exactly this. Let the thought settle the way light settles after a long journey, without urgency, without drama, arriving at exactly the moment the geometry allows. The universe bent the light into rings, and we learned to read them, and what they said was astonishing. Close the books, dim the lamp. Class is over, sleepy scholar.